Here shared in the email, this is a 2-hour workshop. It's a advanced topic workshop. So if you're not familiar with basics of rapid miner, would suggest to watch or join register for our basics workshop. If you have already done through that, it will be great because this is only to cater for the advanced topics. So we won't be going over basics of how to build process and what Rapid Miner Studio is for. So we're just going to learn the concept and how to implement that in Rapid Miner. Right? Having said that, a few housekeeping items here. So hope you got my email. There are few files. For example, it's the complete repository that I have shared um, over the email as a zip file. I'll show you how to import that as a repository in RapidMiner, and we'll use that itself. And if you've not gotten the email, there is something called as a material section on your Guru training window. You could also grab that zip file from there, and hope you have the Studio 8.2 version. And just to reduce the background noise, I've muted everyone. So while I'm going through the workshop, please feel free to chat in. I'm constantly monitoring our chat window. So if you have any questions at any point of the workshop, feel free to chat in. I'll keep monitoring, and when it's a right time to pause, I will just pause and take the question, and we will go from there. Right. So, having said that, this is our agenda for the workshop. So, basically, we will set a base or a ground truth where we discuss why we should validate predictive models. So, why are we validating predictive models? What is the need? And a concept around training and testing errors. What's the difference? Why we should use one against other, and what are the consequences? And we will jump into validation techniques. So two of the very popular or common validation techniques will be discussing. One is split validation. The other one will be cross validation. And as a part of this workshop, I want to introduce a concept called accidental contamination. Yeah, the word looks pretty complex, but when I get there, I'll explain what it is. I'll just give some typical situations or examples. And also, if you're interested in further reading, I will also share a link. There is a blog post regarding that, so I'll share that. But I would just like to introduce that concept since I'm talking about cross-validation or validation techniques. I would also like to discuss this concept of right way of doing validation as well. So this is our agenda. We will get started soon here. So when it's the demo time, I'll just switch to the studio, and I'll also show how to import the repository, the entire zip folder that I have shared. So meantime, if you have not yet downloaded the zip file from the email or from the material section, meantime, go ahead and do that. Well, we are discussing some concepts here, right? So why we need to validate predictive models, right? So often data scientists have been in situations where they think a machine learning model will do a great job of predicting your targets column or something, but once it's in production, it does not perform as well as expected, right? So is it that a model is performing bad, or is it that it's not being validated in the right way, right? So often it's about how the model is validated, and the wrong validation would lead to over optimistic expectations of what will happen in production, right? So it might cost millions of dollars or potentially even human lives if the model is not uh, predicting or performing as expected, right? So it's very, very critical to validate your model and so that you're confident enough that the model will perform in the right way in your um, production, right? So we need a way to validate the model performance. And in this workshop, we'll be mostly concentrating on predictive models, that is supervised learning. Uh, just to just for your knowledge, there are ways and techniques to validate your unsupervised learning techniques as well. But for the scope of this workshop, we will just concentrate on how to validate uh, predictive models, right? So this is a ground truth. Like we need a way to validate our predictive models. So how are we going to do that? What are the pros and cons of every technique, and how are we going to handle that? Will be the main focus of this workshop, right? So before we jump into validation, there are two concepts like training and testing error. So one thing is true for all machine learning techniques, whether it's a decision tree, deep learning, or KNN, we need to know how well a model will perform, right? So we do this by calculating performance matrix. So be it of accuracy or classification error or false positive or specificity, sensitivity. So based on the use case that you're trying to solve, for example, if you're doing linear regression, it would be RMSE, or if you're doing let's say classification problem, logistic regression, something a model is trying to classify, then you are trying to build a performance matrix or a confusion matrix, right, which gives you an accuracy. So based on the model or the use case, for example, it's a continuous variable or the continuous attribute that you want to predict, then you're using RMSE, etc., like for linear regression. Or for logistic regression or classification models, you'll be using mostly the accuracy, confusion matrix, false positive, sensitivity, specificity. So based on what you're trying to build a model on. For example, in the churn use case, if you're doing a classification, whether a customer will churn or not, you're mostly focused on reducing your false positives, right? Like your model should be able to predict your churners better than your loyal customers, because if you lose a customer, that would cost your business. So basically, based on the business use case and also the technique or the modeling algorithm that you're taking, will decide which performance matrix you want to use to test the model accuracy or the model error. Accuracy is nothing but one minus your error or vice versa, right? So that you will use to validate the model performance or yeah, validate the model performance, you would use performance matrix, right? So it could be classification error or any other, as I was talking. So what's the difference between training error and testing error? All right. So if you're calculating, so you can see on my screen here that if you're calculating or you're calculating the model performance on the same data set that you built your model on, that is called your training error. So you're using one single data set to uh, build your model or input to your learner. For example, in this case, it's random forest, and you're applying the same data which is coming in to this, yeah, apply the model on the same data set, and you're calculating the performance of the model. So this would be your training error, right? But for example, if it's a test error, so if the test error is where you're calculating the performance on the test data set rather than on the training data set. So you build a model on the training data and apply that model. So you're applying the model on the test data and calculating its performance, right? So it could be classification error or accuracy, etc. So whichever you choose it to be, or more than one. not only one, but more than one you could do, right? So that is called as a test error. So this is not the real-time data set. It's both the data set will have your target column, and the first data set will be called your training, and the next one will be called the test data set. So it's very important to understand the difference between a training and the test error, right? So training error is calculated by using the same data for the training the model and calculating its error rate or performance in general. And for calculating a test error, you're using completely disjoint data set for both the tasks, right? So why am I talking about all this? So we would have to ignore the training error. Why do I say that? Because you are trying to build a model on the data, and if you give the same data to your um, model, so apply the model and try to calculate its performance, it's obvious that the the model will perform to its best, right? Because it's already seen the data in its training phase, and you're giving the same data to the to validate the performance of the model. So it's obvious that it will be able to perform the best, right? So let me talk in like layman terms. So let's say you are taking up an exam and you write a mock test, and if you're given the same question that came up in the mock test, obviously you will perform 100%, right? So if there is no change at all in the set of questions that you do in the mock test, and also in your final test, then your performance in the final test will be the best. So it's similarly here. You're giving the same data to train the model, and you're giving the same data to see how well the model will perform. So we know that it's critical to validate the model performance on unseen data sets. So there's no point in giving the same data and test its performance. So training error is not helpful at all, and it's also shown in the data in the table here. As you see in the table, we have tried to run different models for different data sets, and also we have calculated the training error and test error. So you can see that how well the model will perform in the training phase, but on the testing phase, it's always that it would do well. It's expected to do well, but yeah, if you see here, you can actually rely on the errors, but on the test errors, but not on the training errors. And you see, there's a lot of so average of almost 10% difference, right, between your training error and testing error. So you will be misleaded if the model is performing the best in the training phase, and you think or you expect it to work the similar way in the uh, testing phase, but no, there's a huge, at least a difference of 10%. So it's highly recommended not to use training errors at all, as they are misleading and they overlay optimistic estimation for your model accuracy or error, right? So any performance matrix, it's always good to ignore whatever you do for the training, because it's not the real truth, right? So you might get misled thinking that the model is performing well on your data set, right? So we would have to ignore the training errors. And so to validate our model performance, so we understood that this kind of training on the same data and applying the model is not the way to go. We need to calculate the test error, right? But is there a technique to validate this model? So the one basic one that we saw was split validation, right? So we split the data set into train and test, and validate. We will validate the model on the holdout or the test data set. So we will let's switch to Studio and build this process, and I'll come back and explain what are the pros and cons of these techniques, and from there we will see what other techniques we have got, right? So let's open our Studio, RapidMiner Studio, as you see here, and let's create a repository. So I guess most of us are familiar with these steps. So I'll go a bit forward. Yeah, so will training error is larger than the testing error. So it again depends on the use case. Sometimes if you think the training error is too high, right? But your model, so training error obviously will be as less as possible because you're feeding in the same data set, so training error will be less. But your what I'm trying to say here is you cannot rely on the training error. So you will be misleaded if you're using the training error to validate your model performance or expect it to work in a similar way on the unseen data, because you are building a model using the same data to validate your model. It is not seeing the real-time data, or it is again going to the same um, data to uh, build a prediction, right? So obviously it will do well, but it's misleading. So it's better you test your model on the unseen data and then put it into production, so that your confidence of it performing better in the production will be high. So that's the reason you would have to ignore training error and use the testing error. Hope that is um clear to you. So let's create a local repository here. Click on next. Uncheck this use standard location. So hope everyone have had a chance to uh, unzip the file here. So there is a folder called model validation which I shared. There is a zip folder. So please make sure to unzip that and keep the repository, unzip repository, and let's go ahead and import that. So it's on one of my folder locations here. So I'll just navigate to that folder location. So here my repository is here. So let's open that and let's give this a name. So here we are trying to open a repository that was shared earlier over the email. So just unzip that. You should be able to get a unzip folder, right? And click on finish. Once you have created that, you should be able to see data and processes, right? Just for your comfort, I have shared the entire repository and the data because we all know how to create processes, save it, and all that good stuff. So just to skip all those here and make use of this time, I've just shared the repository here, right? So coming to the validation techniques that are available on this platform. So if you start typing validation, there is cross validation, split, bootstrap, wrapper split, and wrapper X. So bootstrap is nothing where you're trying to increase the sample ratio. For example, let's say you have very less data, which is very uncommon in these days because we have enough data, millions of rows of data. So usually you won't see usage of bootstrapping these days because you have enough data to build your model. So only when your data is very small, you want to increase the number of samples in your data set, then you would be using bootstrapping. So that's the reason I'm just skipping that. But if there are cases where data is very small, then you could be using bootstrap validation. And as you see here, you can mention the sampling ratio, and you can build your training and testing phase. I'll go in detail on what is each phase there and how it works. So bootstrapping is one, and the split validation is the one that we are going to see now. So as you see here, you would be, I'm just using one of the data sets which was shared. So that is diabetes data set. So let's put a breakpoint and see what this data set looks like. So this data gives us whether particular test for a given patient of age, different age, insulin mass, pressure, blood pressure, and a few other um, tests or values being recorded here. And we have a class where it says whether it's tested positive or negative, diabetes being tested positive or negative. And note that we already have a column which is set with a label role, right? So all any of your model in RapidMiner would need input, training input. So the difference between any example set or training input is that the data will have a column called label. So RapidMiner knows on which column you need to build the prediction on, right? So that's the reason we already have. So make sure you input a data which already has a column of label, right? And as you see here, there are few things, a few important parameters. So you could either split on absolute or relative. So for example, absolute will be how much is your test set size and train set size, and relative would be your percentages. So most of the time it's 70%. So zero point 0.7 is the ratio for your training, and the rest 1 minus zero point 0.7, that is zero point 0.3, will be your test phase. Okay, and the sampling type is either it could be shuffled, so random sampling you can do, or stratified sampling. Stratified sampling will help you sample the data such that it has 70% of both of the representation in your training phase. So what do I mean by that? There are two classes in this, tested positive and tested negative, right? So 70%, the 70% ratio will have equal number of tests and tested negative and positive, and the 30% will have equal number of both the classes. So that's called stratified sampling. So you're making sure you're training your model on balanced data set, for example, right? It will make sure the ratio is almost balanced. Obviously, it can't be equal because it's just using the data that you give. So it will just make sure both of the class are represented equally in training and testing. So that's called stratified sampling. And automatic will just retain the ratio of both the classes, right? So in this case, it's um, so 500 of your samples is tested negative and half of that is positive. So the same ratio will be maintained in your automatic, but in your stratified sampling, it will try to balance out both positive and negative in the training phase, right? and use local random seed. So if you're trying to match your results with mine, then you would be using local random seed. So let's go ahead and use that. And as you see here, it's a process. So you double click. So this is the best part of Rapid Miner. Since it's visually there, you know what's happening in the training phase and you know what's happening in the testing phase. So in the training phase, you just build a model, and so let's say it will first split the data into zero point 0.7 and zero point 0.3. So 70% of your data is used for training your model. So this could be any model, any learner. For example, we have n number of algorithms, as you know. So you could use any of the algorithm here, mostly the classification ones, because you're trying to predict whether a given sample will be like a given row or a record, medical record will lead to positive diabetes or negative diabetes, right? So in the training phase, you're using that 70% and it will train the model. And in your testing phase, it will just take the 30% and apply the model, right? So here we are making sure that there is no leakage of data. So the test phase has never seen your training phase, right? That's the biggest advantage of validation, split validation, and the way it's been implemented on RapidMiner. So you're making sure there's no data leakage between training and testing phase. So train data comes in, the test data is coming directly from your data set here. So we are making sure that you're training on the 70%, test on the 30%. So you will apply that model to the test data, which has not been seen from your training phase, and you will validate your model performance, right? And as you see here, your one unique thing about this platform again is you're not just calculating or validating the performance on few standard ones, but based on your use case or business requirement, you could use other matrices to validate your model performance, right? Other matrix to validate your model performance, and you could also set what is the criteria on which you want to validate. So let's say I pick accuracy, classification error, and absolute error, for example, or square correlation, and I want to build a model whose criterion I want to do on accuracy. So my main criteria is accuracy of the model. So I can set that here and run the model, right? So just I'll uncheck these and let's run this model, classification error and accuracy. And so let's go with the default option, however it was set. And let's go ahead and run this process. So you see that the model performance, the classification error is around 28.26, and also you get the model output, right? So let's try to connect all of this here. Uh, yeah, the model output, for example, yeah, uh, you can see the example set right from here. So you just don't have, you have the predictions and also the confidence values for how this particular class or how it was grouped into this particular class, right? You have the confidence values for that and also this, and you have this errors, and you see that your model is still not doing great on predicting your negatives or positives. So yeah, we are not trying to really see how it's doing well on this data set, but I just wanted to talk about this concept where we use split validation, right? So We are using the given data set for training and testing purpose, and we are using as much data as possible for training, that is 70%, and the rest 30% we are using for testing, right? But yeah, this is all good. We saw how the model is help, like this particular technique is better than just using your training errors. So you get a test error in this, and you are able to validate your model performance. But quickly you can see few disadvantages, right, or the drawbacks. So we split the data into 70 and 30, but how can we make sure it is split in the random way? So as as random it will be subjected to a test where it is like, okay, the validation phase where you have the highest random data so that it can perform well or get trained on the as random as possible and also test on as random as possible. So you want to make your model as robust as possible. So as random it's good because you never know how your real-time data set will be, right? So you want to build your model uh, such that it is robust enough to handle any random data, random sample of data in your real-time scenario or production, right? So since we use just the 30% or if you change the ratios as well, you will use very less data to train. If you want to change, let's say 50% and 50%, your model is not going to do really well if it's getting trained on as less sample as possible, right? So, so if you increase the training errors to 70% and you're just going to test on 30%, the test error might be very less representative of your model performance, that is accuracy or error, etc. So this is a major drawback. Uh, you're not using the entire data available to train your model and test your model, right? So you're splitting the data. The advantage is it's not the data is not getting leaked, but you're not using as much data as possible, right? So that's the reason most often we use cross validation technique, right? So before I jump into the technique cross validation, let's take a quick 4 minute break here since we have enough time. I will talk in detail about cross validation and some key takeaways. We'll also build a model. So let's break for a quick 4 minutes here. Okay, let's resume back here. So we saw how to build a split validation technique, right? So how to split the data, train data and test data into 70% and 30% or any other ratio, and train a model and validate the model performance by applying it to the testing phase. And since it's a visual platform, RapidMiner, you can you can be 100% sure that there's no data leakage, and also um, you can easily build that validation process within this sub process, right? So we did see that, and we did check the classification error, and there are a number of other metrics that you can use to validate your model performance, right? But we also saw a drawback that your model is not trained on enough data because you're just splitting it. And not only that, you're not sure that splitting happens in the random way because you want your model to be robust. So you want to subject your model both in training and testing phase to as randomness as possible so that in production you're confident that the model will perform well, like its predictions are really good, because in production you can't really test the model or validate the model performance, right? You need to build predictions on the real-time data. So whatever you're doing, you'll be doing in the training phase and testing phase, or the validation phase. Make sure it's as robust as possible so that your model performance well in your production, right? So we saw that split validation, you lose some data, and also it's not as random, so it will be less representative of the model accuracy. So the gold standard we call is the cross validation technique, right? So let me give an example here. Like, let's say your data, so it's cross validation or k-fold validation technique, where you divide your data set into k number of folds, as you see here. For example, if you divide your data set into 10 number of folds, so what happens is the first fold is set aside for your testing phase, and the other um, 9 folds, k minus 1 folds, will be used for your training phase, right? That happens in the first iteration. So in the second iteration, what happens is the second fold will be set aside for your test phase, and the rest 9 of the folds will be used for your training phase. So there are two advantages in this. You're making sure you use, so this iteration continues for k number of times, so 10 number of times, so that every fold, so in every iteration, there is a unique fold of your test data, and the rest will be used for your training. So in training phase, it's fine if your data is not being leaked, because you're still trying to train, but in your validation, you just want to make sure it's a unique fold in every iteration. So we are just making sure in every iteration it's a unique fold, and at last you'll be taking the average of all of this and giving out the model perform. The model performance will be the average uh, of all these iterations, right? So, two big advantages: you're not splitting your data, so all of your data is used for training, and all of your data is used for validating your model performance. So, the data you're using it in the best way to train and test your model. And the next thing is there is still no data leakage, because in every iteration, one fold is completely set aside for your validation, which is not seen by the training or the model, the learner, and that unique fold will be used for your um, validating your model performance, right? So there's no leakage of data at all, right? So, and you're not just using one iteration to validate your model. So you're going to use uh, all of, so you're running 10 validation uh, cycles in this, and you get average of your model performance. So it's not just one value or one time you run, but you have average of these values. So it's always better because you have run more than one time, like you have validated your model more than once. So k number of times you've validated, and you're taking the average of that. So your confidence of model being robust is much higher than just running it through one iteration, right? The better, so the more you validate your model on different sets of data and take its performance, average performance, the better is your confidence that it will perform well on your production, right? So two major advantages: you're making use of the entire data to train and validate your model or test your model, and there's no data leakage, and your this technique is more robust than your split validation because you're running k number of iterations uh, or k times your model is being validated, and that average value is taken rather than just one value, right? So if you can open your cross validation, so all that we did, it's been done here is taken your cross validation operator and the same data set we are using, and we are going to build a random forest. So if you want to see how the data is set gets split, let me put this breakpoint after, and let's connect this so that you'll be able to see how the data is split, and you can see in every iteration how it changes the set of data, right? So a few important parameters. So what is leave one out? What leave one out does is, so for example, in this data set, you have 768 um, rows in the data. So leave one out, what it will do is leave one of the example set for validating, and use rest of the data for your testing. So it needs a lot of time to run high computation power because it will run for 768 times, because in every iteration it will consider one column for validation and the rest for training. You might be thinking that in the validation phase or the testing phase, it is going through just one example set. But the other advantage is you're running 768 iterations, so you're validating the model on 768 times and getting the model accuracy and average of that. So it's always there are upsides and downsides of every technique. So we'll leave one out. Will do uh, will perform in this way. But number of folds, again, if we set it to k, it will be similar to what we just discussed. How it will divide the data, and again the same sampling type that was available on split validation. So let's use stratified so that it will make sure the data is balanced as much as possible. So let's use local random seed and run this. So as you see here in the first, so since I've put a breakpoint, it will stop for the output of random forest. So if you see here, it just took 691 of, so as you know, 10 folds. The data will be divided into 10 folds. The 9 folds are being used for training, and the rest will be used for testing. I guess I will have to connect this one now. Yeah, just connect this and now we should be able to get this output. I guess, yeah. So we got the performance one. So the 230 examples which were left out for validation is used for validating your model. So this is the first iteration because as you see here, it will go through 10 iterations and give you the at last will give you the performance, average performance, I guess, if you want to see here. This is for just for the first iteration where one fold was used for um, testing or validating your model. As you see here, one of the fold comes here and the rest folds will be here. And you saw how many examples were taken, right? So this will run for 10 times. So I'll just remove the breakpoint and give it a run. So I guess since I had two of it open, I'll just close all of this and rerun this just to make sure I have the right performance matrix. So yeah, classification error is now around 26%, and you see the model results here as well, right? So let me go back and run this. Yeah, as you saw, it's 28% in case of split validation, and we just changed it to cross validation, and we are already able to reduce it by 2% the error, right? And there are a few other things that we'll have to take care of, whether you want to apply pre-pruning or not, and these things. And so I'm not going to touch upon all that, but there are techniques where you optimize this, and I'm sure most of you will know that by now it's optimized parameters. So you could wrap all of this inside optimized parameter and also optimize these to improve the error. So our focus is just to check which validation technique is best, what are the pros and cons. So not concentrating more on the other techniques and also the performance, but I just want to introduce or um, discuss about the different techniques, how it's easy on RapidMiner, right? Again, since it's a visual platform, you can make sure uh, the training and testing phases, there is no leakage of data in between. So your performance is as close as to reality, and the setup will help you. So if you're trying to code, it will be very difficult. So uh, in this platform, it's very, very easy to do such splitting and also make sure there is no data leakage, right? And also, since it also guarantees that there is no overlap between the k test sets because it's unique in every fold, and it won't introduce any form of negative selection bias, right? So you're not the model is not getting biased because you are making sure that both of the faces have unique data in every iteration, right? So, and another advantage, as I said, it will build an average of the test errors or any other matrix. So you're just not running one iteration, you're running n number of iterations, in this case 10 iterations, and you're taking the average of the performance. That's another best part of cross validation. So anytime you're trying to build validation techniques, your first goal should be cross validation for the obvious reasons or the reasons that we just discussed on, right? And a few key takeaways for validation technique, as we discussed first, never use the training error for estimating how well a model will perform, and always build a holdout data set of your data that's not used for training in order to calculate much more reliable test error, right? So make sure there's no data leakage between your training and testing error. And keep in mind, we are trying to do all of this to build, to validate a predictive model. And we also discussed why it's very, very important to validate the predictive model. Though your model is good, it might not perform best in your production if you have not if you have validated it in a wrong way, right? If you're using training error, it's a wrong way to validate your model and expect it to perform or do a good job in production, right? It's not, you can't rely on that. So not only that you select model parameters, optimum model parameters, it's also very critical to validate your model and build or calculate much more reliable model performance matrix, right? Maybe in this case, a test error, model accuracy, etc. And um, for all the reasons we discussed, cross validation is a perfect way to make full use of your data without leaking information into the training phase, right? Even we had testing split validation, we did see that, but we saw that cross validation is a better technique because there's no leakage of data, yes, and also that you are getting more reliable model performance because you're trying to run that on different or number of iterations and taking the average of the performance, right? So yeah, we did see that process. This is a crossfire. We did go through all of these, and the next thing I want to talk about is contamination. So there are a few processes. I'll also go through that. First, let's talk what is accidental contamination, right? So we saw that it's very easy to leak information between the testing data into the training data about the testing data and to perform cross validation in the wrong way, right? So, for example, let's say I use a normalization in this case, right? Let me explain with an example here. So let's say I normalize this data. So we usually normalize the data, right, to bring it to same level. All the columns have similar range and no column overshadows each other. So we do normalize data when there are different range of values, right? So if I use a normalization just before cross validation, so is this a right way that I am doing? No, because your normalization function or the data, the entire data has seen your normalization technique, right? Uh, so this might lead into wrong estimation. If you normalize the data, as you see here, before the cross validation, you actually leak information about the distribution of the test data into the way you normalize the training data, right? So, and what does normalization do? It will check the distribution of the entire data set and it's going to normalize. So, if you're going to normalize the entire data, before the cross validation, you're already leaking out the information about the distribution of the test data. Though you're splitting it here, but your model is taking the normalized input, right? So the normalized input is, so the training, you're feeding in the training data here, which has already seen the entire distribution of your data. So you have already leaked information about the distribution of the test data into the way you normalize the training data, right? So this is exactly what I'm talking about, contamination. And the effect of contamination is it will lead to wrong error estimation, right? So although you're not using the test data for your training model, you still leak some information about the distribution of data. In this case, it's normalization, right? Or let's say you're doing some um, PCA. So again, PCA has seen your entire data. If you want to use PCA, you're already exposing your data, the training phase into the um, entire data set. You're building components out of it and then splitting. No, there's already leakage of information, right? So some information about um the entire distribution, for example, in normalization or in principal component analysis, what does it happen? It will take weightages and assign that to principal components and build principal components are built based on the weightages of every example set and assigned it to a variable, right? So I won't get in depth to PCA, but yeah, again, you are trying to do some pre-processing step before you're exposing your data into training and testing. So this kind of leads or gives away information about the distribution or how the weightages are there in your test data into your training phase. So this is exactly the contamination that I'm calling the leaking of information of your pre-processing steps due to pre-processing steps, and this will lead to a wrong error estimation, right? So this could be your normalization, for example. Yeah, you could use this. You could open this normalization here, or parameter optimization. For example, you're already giving in information about the number of trees you want to build on the entire data, and then you're putting in cross validation. No, that's not the right way you do. So you might want to consider these contaminations. So just to uh, summarize or brief on what is contamination here. So it provides access to information the machine learning method should not have access during your training phase, right? And with contamination, yeah, the model might perform better than you expect it to perform in your validation because it's already seen your uh, test data distribution or any other features, right? Features of your data is already seen by your training phase. So you might want to avoid these uh, contamination since it leads to optimistic estimation how well the model will perform in future, right? So for the same reasons, there are ways where you can avoid that very easily on this platform, right? If you're trying to code all of this, you can really imagine how complex the code would get, right? You want to make sure you're just doing normalization on the training phase. And the best part is, yeah, so if you have normalized the data and trained your model, obviously if you don't apply the same normalization or the pre-processing step, obviously your model will not be able to recognize those values, right? Because it will be still seeing your raw data, which is not normalized, so it won't be able to build predictions. But in RapidMiner, you can still pass over the pre-processing values. So this will just like the model formula it takes over and passes it to testing, it similarly you can pass the pre-processing pre-processing model, in this case, how the normalization is done, what technique was used, and what is the range that you're applying for each of the column in the data set, that will be passed over. Just like your model formula, you can retrieve a pre-processing model formula for normalization, for example, or if you're using PCA, I guess you did observe, you can pass over this. So you can apply, first you will be applying the model, right? For example, the normalization to your test data. So your test data is coming in here and your pre-processing model is coming here. So first you apply that that output will be applied to your model. So there is no leakage of data at all, right? And let me show you another way. So if you want to build along with me, you can do that. So this is one way of applying, but you see there is some recommended operators called group models. So that you can place on training phase. What will happen is you might want to take the right sequence here. So first you want to apply the pre-processing, and then you will apply KNN models, right? And this together you can apply it to the testing phase. So what will happen is the model will first, so this model output will have two models. One is normalization and KNN. So it will apply to the test data in the order that it was supplied. So first it will apply the normalization, right? And then it will apply the KNN right here to your test phase. So you're making sure that there's no leakage of data, right? So let me just run this normalization before cross validation and see the performance. It's around 26% the error. But let's say in this case, we'll run this and you see it's almost same since the data is very small. But we have seen cases where you run this um, normalization before, then you're leaking some data and the model performance, you're leading to a wrong error estimation, right? So this is a classic example of contamination, and most of the visualization tools out there really don't support a cross validation technique. And if they do, there are no ways to make sure there is no leakage of data or information like pre-processing model information. So this platform really helps you build a robust model. You can calculate reliable model performances because of the reason that you can do all of the pre-processing on the training phase, and you can still pass over the model formula or the function to the testing phase. So let me just put a breakpoint on this group models. So it will, for every iteration, it will just show you. So look at this. It just gave me the Z transform. So it's going to apply Z transformation, and you get the values here. So the same information, just this information is passed over to your testing phase. So the data is not yet been leaked to either of the phases here. So it will just take over the model formula and it will pass it on to the testing phase. And the supply model will apply first the normalization to the test phase, and then the learner formula, that is the function of KNN, will be applied, and you get model predictions. So you know that so you're trying to build a better or robust validation process here, right? So very important. It's just not that you build cross validation. So first we started off saying, okay, we need a way to build a model. Sorry, validate a model. Why? And what are the few techniques out there, split validation or cross validation, most commonly used? We did discuss which is more appropriate or which has a better advantage, pros and cons, right? We did discuss. But is that all? Are you sure you are building a best validation process? No. There is a problem that it would there's a easy way, very easy to leak information if you're doing some pre-processing steps before you uh, input the data into training and testing, right? So yes, we did check that out, and we saw how to handle that, right? In this case, we just put everything on the training phase, moved over the formula to the testing phase, right? But let me also help you understand the optimization. So here, optimization again, similar technique. You're trying to optimize the model for parameters and test its performance. You want to see what best values of the model will give you the best performance. So you'll be running number of iterations to do that. I won't go into details of optimization because I'm sure most of you would know this since you have taken the basic workshop. But in this case, again, you're trying to push like your some of the information is already being seen because it's trying to get the range here and cross validation. So some information is already leaked. So for those obvious reasons, what you can do is inside cross-validation, you're going to optimize in the training phase, you can optimize this. So this is just to this cross-validation sub-process. So let me take a step back here. So you want to implement optimization in the training phase and not on the testing phase, right? So what you will do is put that on the training phase instead of putting it outside as a wrapper. You will put that in the training phase, right? And as you know, optimization will need a cross-validation technique. So this cross-validation technique is just helping you fetch a right optimum value, right? So you're trying to optimize the value. And there are operators that help you just take the values, right? So what set parameters will do is take all the parameters of your model. So in this case, it's a random forest. The operator name is random forest. It will take all of the parameters that was the best for the random forest in this case. It will validate the model performance and optimum value will be fetched. And you can pass that over to the set parameters. So let me put a breakpoint and run this. So for every iteration, what it will do is optimize the few of the parameters, right? Um, yeah, so in this case, it's just trying to optimize the number of trees. Okay, so this 80, the value of 80 will be passed over to your test parameters. So if I put a breakpoint here and run this and see show parameter results. So as you see here, it just copied over the value and this will be applied to your model, right? So you saw that you gave a name to it. So from which operator you want to copy this? It's the random forest. The name of the operator inside this is random forest. So you want to copy the parameters of the random forest and apply it to this one, right? Because again, this is a random forest. So you see the value of 80 is being copied to this, like it will be passed over and that will be applied. So you're making sure you're not um, optimizing on the entire process, but just on the training phase, and you're passing over the model parameters, which is the optimum model parameter, and you're applying that model on your test phase, right? So this is another typical situation where you're contaminating through parameter optimization, right? There are others as well, which are much more advanced, like feature selection, etc. So here we made sure that we are optimizing in the training phase, just copy over the values of that to the model. You build a training model in the training phase again. And so your optimization parameter grid in the training phase has no idea about your test data and it has not built your the selected the optimum value based on the entire data set, but it has selected on just your training phase. So your test set remains just as a real-time scenario where it's more like a production phase, production testing where you don't know how the data would be. You want to use this model and you want to be confident, and these uh, test errors or the model matrices are more robust than just building a model and testing on two different data sets, right? So this is the contamination that could happen. So a few examples, we did see how normalization does contamination, uh, and like leakage of information and feature selection. And if you're interested, go ahead and read this blog post, how to correctly validate machine learning models. This is a blog written by the founder of RapidMiner, Dr. Ingo Mirsva. So very well explained how each of these techniques in detail. It's a, I guess, 22 or 23 page PDF. So if you're interested to know more, do read this, right? And a few quick takeaways again. So if you're using R or Python or any other scripting language, you need to take care of the correct non-contamination validation yourself. Could be complex because you're trying to do so much of coding, and just make sure there's no leakage of information. And it should be modular. That means you can change what happens inside for in case of normalization or parameter optimization. You saw that how there could be leakage of information, and it should be and you should select a technique where it can support multiple levels. For example, in this process, you just saw that there is so much of nesting, right? Cross validation inside that you have optimization to select the best optimum value for a given parameter, the model. So it should be able to support multiple level of nesting, but still keep the process as less complex as possible, right? And yeah, you need a pre-processing model for all data transformation and other model optimization. So we just saw that you should have a way to just pass over the pre-processing steps, pre-processing model formula, right? In this case, we saw how we could pass over the pre-processing model formula. So while you're selecting a platform to build your cross validate or validate, sorry, while you're selecting a platform to validate your model, make sure you check these points because it's very critical to have a platform where you can visually build all this. Make sure it's as less complex as possible. Still support the best techniques so that you are not getting a wrong estimation of your model performance, right? So, having said that, this was the content of the workshop for today. Since we didn't build the processes ourselves, I thought we could just skip that because we are all a pro now by with RapidMiner by for building processes, right? So just wanted to save that time there to make better use of it. That gave me some time to talk about contamination techniques, and we still have 30 minutes left. I'll hang around here for 10 more minutes. If you have questions, do let me know. And if you have some feedback on how this content was, the delivery of the workshop, feel free to chat in here or send me an email. So so that we can do better uh, if needed next time, right? And I will be sharing this deck and the recordings for your use at the just after the end of the session here. And also, if you're interested to attend online workshops, we do have our own conference running called Wisdom. So this is the conference hosted by Rapid Miner in New Orleans. So there are different genres there. We are going to have on hands-on training there, where you can it would be basic or just advanced topics. You can meet us in person. There are data science tracks, business tracks. So if you want to understand how our current customers are using Rapid Miner in their businesses, we will have them talking in this conference. And a good networking place, you would find people from different fields like business analysts, IT, architects, engineers, data scientists, most of them out there. So it will be a great place to socialize with people in the same field, right? And we do have a hackathon. So if you're interested, just go to our website and you can find more information. So it's in October. It's the eighth conference that we are running. So it will be great to connect with fellow rapid miners and uh, great to hear from industry experts who are using Rapid Miner, learn new skills, and we have a lot of fun and hackathon. So yeah, it will be good to see you there if you have some time. Please make sure to attend this. Otherwise, thank you all for joining this session. It was great for me to teach this particular concept. And if you have any comments, feedback, or questions, let me know. And I'll hang around here for 10 minutes and monitor our chat window. Thank you.